Okay, physics. Physics, we have one more section to do, which is section 12.2, which I would like to do today and give you some to try. That means we're going to have a test next week. I'm just trying to figure out what day that would work. I'm having a calculus one on Tuesday, May 12th, so that definitely doesn't work for physics because I don't want to have both of those on the same day. You're welcome. So if we finish today, I'll give you a few to try, go over homework on Monday, give you Tuesday, Wednesday to study, maybe Thursday of next week. Would that make sense? If Thursday doesn't work for you for some reason, if Thursday of next week, that would be the 14th. If Tuesday, May 14th, does not work for you for some reason, please let me know. But as of right now, I'm saying that Tuesday, May 14th would be a great day to finish off this chapter. And then we only have one more chapter left to go. All right? So, that being said, let's talk about this last section. This last section is not very long. In fact, it has a lot of theory on it. Like I said before, the test will be mostly theory. So, we will be doing that via Zoom because it will be a lot of theory, unfortunately, for some of you. Great for others of you. So 12.2 talks about planetary and satellite motion. So in this day and age, there are just a ton of satellites orbiting the Earth at any given moment in time. So whose idea was it to actually put things out there, and how did they figure that out? How did they figure out how to get people into space? How did they figure out how to get a satellite out into space, and not only get it out into space, but get it so that it would actually orbit the Earth? That actually took a whole lot of math, and it took a whole lot of math before calculators. If you have, I keep referencing movies, but I really like movies. If you haven't seen the movie Hidden Figures, it's actually about Black women during the space race time working for NASA and how much they contributed but actually got no credit whatsoever. It will make you angry when you watch it. But it really highlights how many things they had to consider when trying to launch something into space. So when they do the math, they have to figure out things like exactly what trajectory is it going to take? What orbit is it going to take? How high above the Earth is it going to be? How long is it going to take to go around the Earth? Everything is in a decaying orbit because guess what? Gravity does work out in space. It's just a lot less, but there is gravity out there. And so eventually those satellites do fall to Earth. Again, they have to figure out how quickly is that orbit going to decay? When exactly will it fall to the Earth? Where will it be in its orbit when it does that, so that when it falls to the Earth, where will it be? They have to figure out what angle do I have to launch it at so that it doesn't like combust when it goes. How long do the rockets have to fire to give it the exact velocity it needs to be to land, to get to exactly where it needs to get to be in orbit? All of those things have to be figured out. Can you imagine doing that and go, by the way, don't use a calculator? It boggles my mind because I am so reliant on Harriet. It's just crazy. So if you haven't seen the movie Hidden Figures, that is one of the things I was planning on doing with you guys, was taking a few fun days at school towards the end of the year and watching that movie together. And now we're not doing it. If you're bored, try and find it. It's not on Netflix anymore. It used to be on Netflix, but it's not there anymore. So again, whose idea was this? Who thought of this first? Believe it or not, Newton thought of artificial satellites hundreds of years before we ever attempted to put a satellite into orbit. I'm trying to find my marker that I had, and I don't know what I did with it. I really don't know what I did with it. Let me find a different one. So Newton did what we call a thought experiment. In other words, he had no way of actually proving this. He had no way of testing it. So he just thought about it and went, this is what I think would happen. So what he thought about was, he said, you know, if I could put a cannon at the top of a really high mountain and I could fire that cannon horizontally, the cannonball would fall towards the earth. But if I could fire it far enough, because the earth curves, right? Because the earth curves. If I could fire that cannon far enough, when it started to fall, it would fall at the same rate that the earth was turning. And so as the ball was falling, as the cannonball was falling, the earth would actually be falling away from the ball at the same rate. And so the ball would never actually land. He was right. That's actually what's happening. All those satellites are out there, they aren't just traveling around the earth, they're actually falling to the earth. It's just they're falling at exactly the same rate that the earth is turning. A little teeny bit slower, it turns out, which is why the decaying orbit. But it's actually, so all those things out there aren't turning around the earth, they're falling towards the earth. They're just falling at the rate that the earth is spinning, or a little bit less. So they're just in a constant free fall. That's all it is. They're in a constant free fall. So the thing that Newton didn't account for when he thought about his thought experiment was the fact that on Earth there's air friction, and so he would never be able to get a tall enough mountain where air friction wouldn't be a huge problem. Okay, so the air friction would actually slow down the cannonball so that it couldn't go fast enough to be falling at the same rate that the Earth was turning. All right. So from the size and curvature of the Earth, Newton knew that Earth's surface would drop by 4.9 meters over a horizontal distance of 8 kilometers. So for every 8 kilometers this way, the Earth would go down, would turn, would fall away 4.9 meters. He knew that. Okay, this is a horrible marker. He knew that. The problem is that there is air friction. So Newton's reasoning was absolutely correct, but he didn't account for air friction. Although the air is too thin to breathe easily on the top of Earth's highest mountain, Mount Everest, there's still such a large amount of air friction on the object that you can't get the cannonball to go far enough, fast enough, so that it won't fall to the earth. It turns out that you would actually have to be 150 kilometers above the Earth's surface for that to happen. And that is where we send satellites and space stations and things like that. Today, launching satellites into orbit is almost routine, but the scientists and engineers still have to carefully select an orbit. So where am I going to put it? Because they can't put it exactly where another satellite is, so they'll run into one another. Again, see the movie Gravity. The scientists perform detailed calculations to ensure that the orbit will fulfill the purpose of the satellite. For example, some weather satellites orbit over the poles, like the North Pole or the South Pole, at relatively low altitudes. So they're not that high above the Earth, so that they can collect really detailed data. They can be close enough to the Earth to collect that. Since a satellite is constantly moving in relation to a ground observer, the satellite receiver has to track the satellite continually so that it can capture the signals that the satellite is sending. In addition, the satellite is on the opposite side of the Earth for long periods of time, so several receivers have to be located around the globe to collect the data at all times. So again, if your satellite's over here, here's the Earth, but your receiver's over here, that's not going to work. So they put receivers all over the Earth so that it can be constantly receiving information. Now, communication satellites and some weather satellites don't travel at a different speed than the Earth. Like these satellites where they're turning, and so if the receiver's over here, there needs to be other receivers over here to catch the signal because it can't go through the Earth. There are other satellites that are in what's called a geostationary orbit. A lot of like communication satellites, so one's for television, one's for your cell phones, those types of satellites are actually in what's called a geostationary orbit. And what that means is they stick them out above the equator, actually. So here's the equator. So it actually spins around the Earth at the same rate that the Earth is rotating. So it looks like that satellite actually never moves, so that they only need one receiver in this spot, because as the receiver moves around, so does the satellite, and it can continually get information from that one satellite. So one receiver, one satellite. So it constantly receives a signal from the satellite. So how do we figure out where that orbit should be? There's a formula for that, and we're going to do the math for that. All right, so this is where we're on page 589, and it says, at what velocity and at what altitude does a satellite have to be in order to be geostationary? Because there is a very specific altitude and a very specific velocity that it has to go in order for it to be geostationary, moving around at the same point all the time. So we want to know the velocity and we want to know the altitude or the height, all right? So we know if it's in a geostationary orbit, that means it has centripetal force, right? There's a centripetal force keeping it in that circle. What is the centripetal force? What supplies that centripetal force? Well, it is the force of gravity. So centripetal force has to equal the force of gravity. What is the force of gravity? The force of gravity is not mass times gravity, because we're talking space. So it is G m1 times m2 over r squared is equal to centripetal acceleration, which is m times v squared over r. So again, let's talk about what those letters actually represent. G, 6.67 times 10 to the negative 11th, that is the universal gravitational constant. The two m's, one of these m's is the satellite. The other mass is the mass of the Earth, because those are the two objects involved here. The radius, here's the Earth, here's the satellite. The radius is the distance from the center of the Earth out to the satellite. That's the radius, okay? So over here in centripetal acceleration, in centripetal force, the mass is the mass of the object that's doing the spinning. So that would be the mass of the satellite times the velocity of the satellite squared over r. R being the same as this r. Because I have a mass of the satellite here and a mass of the satellite here, those I actually get to ignore. Okay. have this. Okay, now the thing is, we know the mass of the Earth, but we don't know the velocity and we don't know the r. That's a problem. That's a problem because we can't have two unknowns. So they say to eliminate r from the equation, we use the equation for the definition of velocity and solve for r. Okay. They're actually going to, I should have looked at this a little closer. They're actually going to derive a brand new formula here. They're going to derive a whole brand new formula here. And so if you want to look at that, you can. So I'm just going to kind of describe what they do, but if you want to see it more in depth, you can look on page 590. So the problem is I have two unknowns. So what they do is they take the fact that there's an r, and they use the formula v is equal to distance divided by time. And the distance is actually the distance around the Earth, which is the circumference of the Earth. And so they use that knowledge, and they figure out a brand new formula. So they take this, they rearrange it all, and they come up with a formula based off of this. They come up with a formula that looks like this. Velocity is actually the cube root of g. Actually, let me do it this way. The cube root of 2 pi times g. Now, in this case, times mass of the Earth, because that's what the satellite is going around, okay? If we were talking about something else going around a different planet, then we would be talking about the mass of that planet, all right? So if we were talking about putting a satellite around Mars, then it would be the mass of Mars that you would have here. It's the mass of whatever the satellite or the thing that's going around, the mass of that, okay, over period. How long it takes it to go around, okay? So they've taken this, rearranged it using their knowledge of things like velocity is distance over time, and the fact that the distance has to do with the circumference of the Earth and all of those wonderful things, that the distance it's going is a circle, which is 2 pi r. So they've used all that, and they have come up with this formula for velocity. So here's a brand new formula, okay? So we want to figure out velocity. So we are going to do the square root of 2 pi times 6.67 times 10 to the negative 11th times the mass of the Earth. I'm running out of space. So times 5.98 times 10 to the 24th. I told you I'd have that memorized. All divided by the period. Now let's talk about the period. If this is a geostationary orbit, that means it's turning with the Earth. So how long does it take the Earth to spin around once? Not go around the sun once. It takes a year to go around the sun. But while it's going around the sun, right, it's spinning. So how long, it's a very fancy spin, how long does it take it to spin? Please be saying 1 day. Please be saying 1 day. Okay, so it takes 1 day for the Earth to go around. So that means the period is 24 hours. In 24 hours, there are 60 minutes, and there are 60 seconds in a minute. So I would do 24 times 60 times 60, which is 8.64 times 10 to the 4th seconds. So my period is 8.64 times 10 to the 4th seconds. So it's the cube root. It's not the square root, it's the cube root. So I'm going to do 2 times pi times 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th. I would hit equals at that point. Then I would divide it by 8.64 times 10 to the 4th, and then I would take the cube root of that. Turns out that the velocity is 3.07 times 10 to the 3rd meters per second. So if you want a satellite to be in geostationary orbit, that's how fast you have to get it to go. Now, to give you some perspective, because I don't think in meters per second, if you convert that into kilometers per hour, that's actually 11,000 kilometers per hour. 11,000 kilometers per hour, okay? We drive, fastest we should drive is about 110 kilometers per hour. Satellites are going 11,000 kilometers per hour. All right, so that is for figuring out the velocity. Now, we want to know what is the height above the Earth's surface that the satellite is. How high above the Earth's surface is it? We want to know a height. So we're going to get another new formula. And again, it is based off of all of like the idea of circumference and what the velocity is. So here's a new formula for you. R is the velocity times the period divided by 2 pi. So the radius is the velocity, how fast the satellite is going, times the period, all divided by 2 pi. That is my R. Now let's talk about what R is. The question asks me what is the height. In other words, from the Earth's surface up to the satellite, how far is that? When we figure out R, we are figuring out the distance from the center of the Earth all the way out to the satellite. There's no formula for figuring out from the surface of the Earth up. There's no formula for that. So all you can figure out is from the center up to here. So if we're going to figure that out, R is the velocity, which we just figured out is 3.07 times 10 to the 3rd meters per second, right? And you have to use the meters per second, times the period. We figured out the period is 8.64 times 10 to the 4th seconds, has to be in seconds, divided by 2 pi. Turns out that the radius is 4.2249 times 10 to the 7th meters. Okay. Turns out that is the R. So that is the distance from the center of the Earth all the way out to the satellite. But I just want to know, if I'm standing on the surface of the Earth, how far away is that satellite? So to figure out the height, I'm going to have to take the radius, which is 4.2249 times 10 to the 7th, and I'm going to have to subtract what the radius of the Earth is. That's on that table that I gave you. It's 6.38 times 10 to the 6th. So if I subtract those two, what I'm left with is this height right here, which turns out to be 3.59 times 10 to the 7th meters. If you don't think in meters very well, I don't. In kilometers, it would be 3.59 times 10 to the 4th kilometers. I don't think in scientific notation very well either. So 1, 2, 3, 4, 3, 5, 9, 0, 0, 35,900 kilometers above the Earth. That's where that satellite is. Okay? So I'm going to give you a few to try. Again, two new formulas there. And if you know the formulas or can use the formulas, it's just a matter of putting the numbers in. All right, a little bit more theory and I'm done talking, I promise. Okay, so when you're out in space, you've all seen the movies, the shows, where the astronauts are floating around because they are quote unquote weightless, right? Actually, astronauts, people from NASA don't actually use the term weightlessness. They do when they're talking to the general public, but that is not a term that is accurate because you're not actually weightless when you're in space. There still is gravity out there working on you, so you actually still have weight. And actually the gravity is quite close to 9.81 even when you're in space. So your weight does change, but it doesn't change as much as you think it does. So they talk about this. I'm looking at page 592. It says on Earth, gravity is 9.81. So if you have an astronaut who weighs 65 kilograms, his weight on Earth would be 65 times 9.81, which would be 638 newtons. Out in space, it's actually only 594 newtons. So not that much difference, 638 to 594. There's not that much difference. So why do we say you're weightless? Because you're not. Think back to your calculations of apparent weight in chapter 5. And remember, apparent weight is when you're standing in the elevator and you've got a scale in the elevator, and if the elevator goes down, it actually takes a second before you start going down. And so for a second, your weight registers as lighter than you actually are because the scale starts falling before you start falling. It says when the imaginary elevator that you were riding was falling, the scale you were standing on reads 0 newtons. Your apparent weight was 0 because you, the scale, and the elevator were falling with the same acceleration. You and the scale were not exerting any force on each other. The same situation exists in the space station and all orbiting spacecraft all of the time. So, like Newton's cannonball idea, everything falls to Earth with the same acceleration, but Earth is falling away equally fast. So the Earth is turning and the satellite is falling. They're doing it at the same rate, so it never actually gets there. So they're not actually weightless, they're just in free fall all the time. That's what weightlessness out in space actually is. It's actually constant free fall is what that is. And so some physicists don't like the term weightlessness because it's not accurate. That's not what it is. So they actually refer to that as microgravity. And that's the word that they use. So if you hear the word microgravity, it's that idea of weightlessness, but you're not actually weightless. You're just falling at the same rate that the Earth is turning. So the Earth is falling away from you at the same rate that you are falling towards the Earth. All right, one more idea, and this is the idea of something called perturbing orbits, which sounds weird. If I perturb you, I annoy you, so perturbing orbits sounds funny. So in all of the examples that you've studied to this point, you've considered only perfectly circular or perfectly elliptical orbits. So, such perfect orbits would occur only if the central body and the satellites were totally isolated from all other objects, if there was nothing else around. Since this is essentially never achieved, all orbits, such as those of planets around the sun and moons and satellites around planets, are slightly distorted ellipses because I need space. Because if you've got the sun path marker. If you have the sun and you have the Earth going in a nice perfect ellipse around it, if there were no other planets out there, nothing else out there, then yeah, the Earth would go in a perfect ellipse, but that's not the case. So you've also got other planets out there. So the next one is Mars, right? So Mars is out here. Mars is actually going to affect our pathway a little bit because Mars is another planet and it has its own gravitational field. So when Mars gets close to Earth, those two actually pull on one another. And so while the sun is pulling Earth towards it, Mars is also pulling Earth towards it. And so what happens is Earth kind of goes off a little bit. It kind of does a little thing, right? So there's always this push and pull from other, pull, because gravity pulls. There's always these pulls from other celestial bodies out there. There's always pulls from other objects out there, other planets, moons, those types of things. So they talk about the moon. For example, when an artificial satellite is between the moon and the Earth. So here's Earth, here's the moon. If you've got a satellite in between those two, well, the moon is going to exert some pull on that, and the Earth is exerting a pull on that. That's going to, it's going to affect the pathway a little bit. So imagine all the math that they have to do because they have to account for that when they figure out the math for the pathways. Imagine how complicated it gets. We're doing perfect, ideal situations, and of course that never actually exists in real life. When a satellite is on the side of the Earth opposite the moon and the Earth exert their forces in the same direction. See, right now the moon pulls this way and the Earth pulls this way. But when the satellite's over here, now the moon is exerting a pull and the Earth is exerting a pull. So now they're both pulling in the same direction. So that's going to affect the pathway. The overall effect is a very slight change in the satellite's orbit, and engineers have to take all of this into account when they're trying to put satellites out into orbit. In the solar system, the planets all exert forces on one another, like I said up here with Mars and Earth. And so each planet perturbs or affects slightly the orbit of all the other planets. In some cases, the effects are so small that we can't even measure them. Astronomers can, however, observe these perturbations, there's a word, in the paths of the planets when the conditions are right. In fact, did you ever think about how did we know before we had all this fancy astronomical, like big, huge, like Hubble telescopes and things, how did they know that Pluto was way out there? How did they know that all these planets were way out there? How did they figure that out? It's because of these perturbations, actually. In fact, in 1845, two astronomers in two different countries who did not know one another, they both individually observed perturbations in the orbit of the planet Uranus. So they knew the path, the elliptical path that it should be taking, and they noticed it kind of moved in a way they didn't expect it to go. And so two different astronomers, two different countries, both noticed the same thing. British astronomer and mathematician John Couch Adams and French astronomer Urbain Jean-Joseph Leverrier couldn't account for these perturbations of the planet's orbit, even by calculating the effects of the gravitational force of the other planets. So they said, we know there's other planets. We know about this planet and this planet and this planet. Those wouldn't do that. So they said there has to be something else out there. There has to be something we don't know about yet out there. And so based on the math about what path did that actually take, what perturbation actually happened, they looked in the area where they thought that there should be something affecting the pathway of the planet. It turns out there was something there. Remember, it's a big sky. You're not always looking in the right place. So they looked where the math told them to go look. Math is amazing. And what they found was a planet that they had not known about. Turns out it was Neptune. So they didn't know about Neptune before that. But they found Neptune because they saw this other planet doing this weird motion thing. About 50 years later, a US astronomer performed calculations on the pathways of Neptune and Uranus, and they discovered orbits that were perturbed again, and so they said there must be another planet out there, probably even further away. Turns out that was Pluto, which I don't know if it has planet status again or not. It was a planet, then it wasn't, but I think it's back to being one. I'm not sure. So they found Pluto in pretty much the same way that they found Neptune. They noticed these perturbations in other planets' orbits and said, okay, there's got to be something that we don't know about causing the planet to move in a way we didn't expect it to move. Since the discovery of two planets that were predicted mathematically by the perturbation of orbits of known planets, several more predictions about undiscovered planets have been made. None have been discovered, and most astronomers believe that no more planets actually exist in our solar system. The laws of Newton and Kepler, however, have provided scientists and astronomers with a solid foundation on which to explain observations and make predictions about planetary motion, as well as send space probes out to observe all of the planets in our solar system. Because remember, if they've sent probes out, they have to know when they send that probe out what trajectory it needs to take to get to the planet they want to get to, because they have to know when is it going to get there, because they have to know where in the elliptical orbit is the planet going to be when the probe actually gets there. Because if they sent a probe out to hit Mars, but Mars was way over here at the time in its orbit, that wouldn't work very well, right? So they have to do all the math to make sure that the probe is going to get to the spot where Mars is actually going to be at that particular time. So there's a lot of math involved. We have just touched on like the basics of it, but this is where it all starts. So this is the end of section 12.2. I will upload the PowerPoint that goes with section 12.2, and I will give you a few questions to try. Again, test on Thursday unless that doesn't work for some reason. All right, test next Thursday. Oh, have a good long weekend.